everybody, it is I, Richard Blyle, your all-time favorite. Well, anyway, I'm here with the third of 4 videos as I like to call them, on the laws of thermodynamics. This one has been a couple weeks, sure made it a couple weeks ago, but hey, like my ex-wife used to say, better late than pregnant. We have, I promised you this, that you would understand these laws based on your own personal experiences. And I hope so far you have, and that's not going to change. It's still true today. I also promised you that I was going to kind of blow your mind a little bit. Well, this is the law that is going to really blow you away. This is the law that is going to just... I hope you're ready. Get towels ready, because, you know, when your mind is blown, it can get a little bit messy with the blood and whatnot. Okay, so let's zoom in on my all-time favorite teaching tool, the chalkboard. How's that? That's pretty good. All right. 0th law of thermodynamics. We discovered that heat flows from a region of high temperature to a region of low temperature. I'm living that today. This is my 2nd floor in my house, and it is very hot. So yeah, that happens. But the heat up here is okay. That's more because of density than anything else. But anyway, yeah, the heat flows from high to low temperature. That's the 0th law of thermodynamics. The 1st law of thermodynamics, and I misquoted it in the last video, so I apologize for that. If you look at the 1st law of the video and it does not say this, that's because I re-recorded it and reposted it. But I accidentally confused the law of conservation of matter with the law of conservation of energy. 1st law of thermodynamics is the law of conservation of energy, which says that energy cannot be created or destroyed, but it can be converted. We talked about converting energy to work and work to energy. The 1st law of thermodynamics also tells us that things tend to go from high energy to low energy. All right? Which is also true. But it's not the whole story. If you have paper and you burn paper, that's happening because the internal energy, which we called enthalpy, if you remembered, it was enthalpy, which is symbolized with a capital E, that is going from high chemical potential to low chemical potential in the ashes. Gasoline, papers, any kind of fuel has very high stored chemical potential energy. Oxygen, oh my God. You have no idea. Oxygen has a lot of stored chemical energy. Combine the two and you end up with products that are low chemical energy. That's 1st law. That happens naturally, but it's not the only thing. As it turns out, if you take ammonium chloride, which is a salt, 2 peanuts are walking down the road, one is assaulted. If that salt happens to be ammonium chloride, take ammonium chloride and you put it in water and you stir it up, that solution becomes very, very cold. Heat is released because as you go from high energy to low energy, that difference in energy goes out into the environment. Well, in this case, we're starting at low energy and we're going to higher energy. That ammonium chloride in solution has higher energy than the salt, which means it's absorbing heat. So it's going from low energy to high energy. So if things tend to go from high to low energy, that shouldn't happen. So there has to be something else. There has to be something happening that is different, that is more than just the energy. That something different we call entropy. Given the symbol capital S. The 2nd law of thermodynamics is one of the most frequently misquoted, certainly one of the most misunderstood laws of all the laws. It's just people don't understand it. I recently heard a very famous, well-known, supposedly high-end scientist talking about the second law of thermodynamics, and he got it wrong. And I mean incredibly wrong. Just very, very wrong. We're going to talk about what the second law actually is. But science, it's like a yin-yang. Okay? Energy tends to go from high to low. Entropy tends to go from low to high. Alright? What is it? Most people think entropy is disorder. Alright? They think that the higher the entropy, the greater the disorder, but this is a bad definition. It's fine to think of it that way, but it's just a bad definition. Because first of all, there's no way to quantify disorder. You can't even quantify dat order. So why can you quantify disorder? Anyway, the other thing is, so there's no mathematical equation for it, and there's no, what you think of as a disorder, I might not. If you have kids, or if you've ever been a kid yourself, parents love to complain about what a mess kids' rooms are. And the kid will usually come back and say, it's fine, I know where everything is. So who's right? It's better to think of entropy in terms of information knowledge. Okay? I have a tattoo of this. I love this. In quantum theory, so we're leaping way ahead now. In quantum theory, entropy is equal to a constant. This is Boltzmann's constant, so sometimes you see it with a subscript b, not always. It's just a constant, it's well known. Times the natural log. Natural log is just a mathematical function. If you have a calculator with logs, I can guarantee you it has a natural log. Log is log, natural log is ln, and the difference is the base. The log key is base 10, ln is base e, which comes up in a lot of natural processes. That's why it's called the natural log. W is the key to the whole thing. W is the size of phase space. Look around your room right now. How many things are there? W represents the total number of possible ways to organize those things. The higher W, the less likely someone can guess what you have done with it. For example, suppose I give you 3 cents and you want to guess how many different coins, how many different possibilities of coins I could give that to you. Well, if you're an American, if you know American money, which you may not, I understand that, but if you understand American currency, there's only one way for me to give you 3 cents. That's to give you 3 pennies. W equals 1. If you put in your calculator 1 and hit ln, you're going to see this becomes 0. Because you know exactly what I'm giving you. But if I give you 5 cents, I could give you 5 pennies or 1 nickel. All of a sudden, you have ln of 2. Now, we're not going to worry about it. You can punch it in if you want, but it's not going to be 0. If I give you 15 cents, I could give you a dime and a nickel, a dime and 5 pennies, I could give you 10 pennies and a nickel, or I could give you 15 pennies. There are 4 ways. Put 4 in there and you get a larger number than 2. Which basically is telling us if I were to guess the combination of coins you're giving me, it's less and less likely I'm going to get the same number, the same coins that you actually are going to hand me. I know less about what you are giving me because there are more possibilities of how you can do it. This is really what entropy is. And you might say to yourself, well, how do you do that for a chemical system? well, W becomes enormous. Because all of a sudden we're talking 600 billion trillion atoms. And we can organize those 600 billion trillion atoms in different ways, and we can assign different energies to each one of them, all of which gives us W. Will we ever actually calculate W? No. The calculation becomes enormous and impossible to do. But conceptually, because of quantum theory tells us that energy levels are quantized. So because of quantum theory, this, in principle, is a finite number. It may look infinite to us, but it's a finite number. So, at least with this definition, which I have in a tattoo on my back, at least there's a real number to it. You can actually do it. I'm looking for lighting that doesn't make me look like a ghost. Oh, that's pretty good, but the problem is you can't see at the board if I do this. How's this? Is that better? Alright, fine. I'll just do this. So anyway, one of my favorite definitions of entropy is this. If you put a drop of wine in a barrel full of sewage, you get a barrel full of sewage. But if you if you put one drop of sewage into a barrel full of wine, you get a barrel full of sewage. If we knew exactly where that one drop of sewage was going, we'd still drink the wine. If we could guarantee that it was always right there and did not diffuse at all, we'd still have good wine. But we don't, do we? Because that sewage is going to disperse out and we're not going to know where it is. So any wine we take out of that barrel is probably contaminated. That's the second law of thermodynamics. That's entropy. Entropy is the yin to the first law's yang. It is the second driving force for any process. And yes, you can say that it means that things are going to more disorder. But you don't have to. The way that we know that entropy is real, there's a hypothetical machine called the Carnot cycle that basically mathematically demonstrates what entropy is. But here's another example. Suppose we were to make a machine. We have a pool of water up here. We're going to let that water drip out into cups. Into a pool of water down here. And we're going to put these on. I made my pool of water too large. We're going to put these on a hinge. So we're going to have a gear up here. We're going to have a gear down here so that this chain can run. As these drop their water out down here, we're going to refill. Just move this a little bit. We're going to fill this, and we're going to have empty cups coming back this way. The weight of the water here should keep this chain moving in this direction. And because it's connected on the other side, the chain should move up this way. And as it goes back around, I'm doing this wrong, aren't I? This will keep going until the one, okay, I'm doing this wrong. I need to reverse this. These cups need to refill the top one, not the bottom one. Okay. Well, here's something that was proposed by Leonardo da Vinci. Suppose we have a pool of water here at the bottom. And what we're going to do is take a very long, slow pathway back to the top. Like this. Now, Da Vinci was thinking this could be miles upon miles upon miles. Which means that the grade, as you go from the bottom to the top, is so slight that it just fills up naturally. And this is going to fill into the top reservoir. The top reservoir, which is what I should have been doing in the first place. Which then will feed into the bottom reservoir. This was Da Vinci's attempt. This was his thought at what's called a perpetual motion machine. Now, a perpetual motion machine, if we could create it, would be a game changer. A perpetual motion machine would give us, if we could bleed off just the slightest amount of energy from this. Okay? So this is a perpetual motion machine because as the water refills, it's going to go along this pathway and refill the top, and the water will continuously flow because the grade here is so small. Okay? So we're not talking about it going up a hill like this, we're talking about it going up a hill like this. The water wouldn't see it, it's so small, if you can make it big enough. In principle. If we could put a little electric generator here to bleed off a little bit of this energy, doesn't matter how small the amount is, if we could bleed any energy off at all, we would have an infinite source of energy. This may be too small to do anything with, but then we can build thousands, hundreds of thousands of these machines. Add them all up and all of a sudden you're talking about real energy. This has been a dream of physicists and humankind for thousands of years. Thousands of years. And there have been many, many, many different attempts to make perpetual motion machines using magnets that attract one way and repel the other, and as it goes around, it just keeps going through these repulsions and attractions, it keeps it moving. Mechanical ways, so if you have ball bearings inside a wheel, and the wheels have little flappers on them, so the ball bearings move this way to turn it this way, and then this way when it's going back up, it's going to keep going forever and ever and ever. Perpetual motion machines have been a dream amongst the most brilliant minds in history. Isaac Newton, Leonardo da Vinci, they all had ideas and tried to make perpetual motion machines. But it can never happen. It can never happen because of the second law of thermodynamics. How do we know that the second law of thermodynamics is true? Because they've never succeeded in making a perpetual motion machine. Doesn't that blow your mind? We talked about this in an earlier video, and I said, look, you can never prove anything in science, you can only disprove it. You cannot prove any of these laws of thermodynamics. The second law of thermodynamics is a law because we have never been able to prove it wrong. That's all. The first time someone creates a perpetual motion machine, all of the laws of thermodynamics collapses, which means everything we think we understand about science, we go back to the drawing boards. Now, are we ever going to prove the second law wrong? No, we are not. We are not, because, well, I'll say it, I don't believe we'll ever be able to make a perpetual motion machine. We would have by now if we could. So I believe this is true. And it's the second driving force. So in that ammonium chloride example I gave you, the internal energy is increasing. That's why it's endothermic. That's why the temperature goes down instead of up. But the entropy, as we go from nice ordered crystals to, if you would like, highly disordered solution, the entropy is increasing. Entropy is the second equation, and entropy always tends to increase for natural processes. Energy always tends to decrease. Entropy always tends to increase. When they work together, something becomes higher in entropy and lower in energy. That's a very vigorous reaction, like dynamite going off. But we have examples where the energy goes down and the entropy goes down, like water condensing into ice. And we have examples where the energy goes up and the entropy goes up, like ammonium chloride dissolving in water. In order to understand what entropy is, and we've talked about this in an earlier video, but let's review. There are three, in anything we consider, there are three things. We have the system, the system is simply the region of space under consideration. So if I want to talk about the water inside my bottle here, that becomes my system. It's what we're talking about. It's what I'm drinking. Systems can also be esoteric. Living organisms, for example. We can be talking about, and I don't know how you feel about evolution, we're going to talk about it here, and I'm not going to say that I believe one way or the other, but evolution can be considered the system. Species evolving is a system, okay? So it doesn't have to be something closed that you can physically hold. It can be, you know, kind of a conceptual system as well as a real system. Outside of the system, we have the surroundings. So, in this system, the surrounding is everything that is not inside the bottle. We have the system, we have the surroundings. And the surroundings can extend as far as you want. But you add the two together and you get the universe. The universe is the system and the surroundings. It's everything. Everything. So entropy, which can be thought of as a state of disorder, actually the best definition I ever heard from entropy comes from when I was in college. My mother bought me a collegiate dictionary because it was on sale because they had the wrong copyright year printed on the inside, so they were selling them dirt cheap. So I got one and I looked up entropy, and it said entropy is the energy used by a system in a process. So if I take this water and I boil it to convert it from a liquid to a gas, the entropy is used for the internal rearrangement of the water molecules as it goes from one state to another. What a great definition. It's used internally. It's the cost of what you're doing. It's the cost of your work. The equation. I promised you an equation for each of these. Okay, let's do it. You may remember delta. Delta means change in. Okay? Always final minus initial. The final entropy minus the initial entropy is delta S. Okay? Change in entropy, you can prove, we're not going to, is always greater than or equal to the change in heat divided by temperature. It's a very simple little equation mathematically, and we're not going to go into any more examples of this, but this is from classical thermodynamics. The last equation I gave you was from quantum theory. This is classical thermodynamics. And notice we're not talking about absolute entropy here. We're talking about change in entropy. Always greater than or equal to the change in heat divided by temperature. The second law of thermodynamics says this. And this is where that other really big name professor, if he sees this, he's going to be pissed off because he got it wrong. And if you saw the video, you might be pissed off too. And that's okay because he said it wrong. And I don't blame him. You know, he's an astrophysicist. He's not really a thermodynamicist. So this is not his field. It's possible he just made a dumb mistake like I did in the last video. Or it's possible that his advisors told him this is the question they're going to ask and here's the answer, and they gave him the wrong answer. Because we don't know everything. Nobody knows everything. He has to have advisors. So it's possible he was told the wrong thing. He said that the second law of thermodynamics says that the entropy of the universe, of a system, the entropy of a system can never decrease, but the entropy of the universe can. That is ass backwards, buddy. That is just wrong. The reality is the second law of thermodynamics says that the entropy of the universe can never, never, never decrease. Okay? The entropy of the universe can never decrease. Now, here's why this is often got mistaken. This is why this is often misspoken. A lot of people will say the second law says entropy can never decrease. Well, that's wrong. Entropy can decrease. But you have to put work into the system in order to make that entropy decrease. I'll give you some examples of that in a minute. But if the entropy of the system decreases, the entropy of the surroundings must increase to make up for that difference. And the entropy of the surroundings must increase enough so the entropy of the universe remains constant at best, which it never does, or increases. So we have to increase the entropy of the universe, no matter what we do. That's the second law of thermodynamics. If the entropy of a system could not decrease, we'd be dead. Think about it. If entropy is lack of knowledge, where is, in the room here, in the air, where are our water molecules? We don't know, do we? That is the absolute least amount of knowledge we can have. We can't take tweezers and pluck a water molecule from here and a water molecule from here. We don't know where those water molecules are. They're dispersed throughout the room. As a liquid, all of these water molecules are confined to this volume. I know exactly where these water molecules are. My knowledge is increased, which means the entropy has decreased. As a solid, now of course, I don't know where in this smaller volume those water molecules are. They're all close to each other, but they're randomly moving around. If I had ice water in that ice, those water molecules are stuck. I only need to know the position of 3 water molecules, and because of the crystal lattice of ice, I can find every other water molecule in that ice cube, or ice chunk, or whatever it is I have. That is a lot of knowledge. I only need 3 to find all of the rest. That is the lowest possible entropy. If entropy can never decrease, water vapor would never be able to form liquid again. The vapor would always be vapor, and if we can't form liquid out of vapor, we wouldn't have rain, because rain is simply water that had accumulated from vapor. And if we don't have rain and water evaporates, eventually everything is arid, it's a desert, and we all die. But here I am, talking to you, sounding like an asshole. So obviously, entropy of a system, if we consider the water in the world our system, entropy of a system has to be able to decrease. But as it does that, it turns out condensation releases heat. And as it releases heat, the molecules around that condensation speed up. And because they're moving faster, we are less likely to know where they are. So the entropy of the surroundings increases. I promised you that the laws of thermodynamics were not restricted to chemistry. Right now, everyone's favorite seasonal state flag has come out all over the United States in the form of orange traffic cones. Over the winter, water seeps into, actually over the year, water seeps into cracks in the concrete, in the roads. When the cold weather comes, that water freezes, and water is one of only 2 known substances to science that expands on freezing. Isn't that amazing? It's the only compound. The other one is an element. Water is the only compound that expands on freezing. It's the only one. If that didn't happen, we wouldn't be alive today either, because all the ice would form at the bottom of the oceans. There could be no plant life in the oceans, and we never would have evolved. Think about that. Anyway, as that water freezes, it expands, which cracks the concrete, which causes all of those potholes and cracks and everything that's such a nuisance to drive over. So what do? If we define our roads as our system, if we define our roads as our system, we have to do construction. We do work on the system to decrease the entropy. We don't know where all those potholes are. We find them in most annoying ways as we drive through. First time we hit one, oh God, hope I didn't damage my tires. Very, very high entropy because we don't know all the damage that has occurred. So what do? They fill in the potholes, or they dig up the asphalt and lay fresh asphalt down. They are decreasing the entropy because they're fixing the roads. But as they're doing that by doing work on the system, but how do they do that? They do that with those big machines. They do that with bulldozers and concrete mixers and all of these machines that burn petrol, as my friend in Scotland would call it. They burn gasoline, which converts liquid into carbon dioxide gas. The entropy, as they spew that out into the environment, the entropy of the surroundings as they're working on the roads is increasing. Increased entropy in the surroundings plus the decreased entropy of the roads, the entropy of the universe actually must increase. Like I say, or remain neutral, which it never does. That's an ideal situation. There's no such thing. Ideal situations are like ideal men. They're fun to think about, but ask any of my female friends and they'll tell you they just don't exist. Says a guy. So entropy. In the second law of thermodynamics, the second law of thermodynamics says the entropy of the universe can never decrease. Entropy can decrease. The entropy of the system can decrease. But the entropy of the universe cannot. People have tried to use this as an argument against evolution. Now, I'm not going to tell you what to believe. I hear weird little things like, if water did not increase when it freezes, we wouldn't be here today because plant life could have never taken root in the bottom of the oceans. Couple that with the fact that the only compound that freezes, that expands on freezing, is water. You know what? That's really hard. Okay, you can say, well, that's coincidence, but I find it... I'm one of those people who believes in God. I do. You can laugh if you want. You're not going to change my opinion. But I don't believe, I still believe in evolution, let's put it that way. I still believe in the laws of physics and chemistry, even though I believe in God. I think that they can happily coexist. That's my personal opinion. You don't have to agree. But I will tell you this, people who say that because of the second law of thermodynamics, evolution is impossible, they're wrong. The argument is wrong. Not what they're arguing. But you can't use entropy, the second law, against evolution, because the fact is we are the most evolved species on the planet. We are the ones who have been digging coal and fossil fuels and oils out from the ground and pumping them into the carbon cycle on Earth. You go from a solid to a gas, that is a huge increase in entropy. And because we are evolved enough to do that, we are going to kill ourselves with global warming. That means that the entropy of the universe is indeed increasing because as a species, our entropy decreased. Because we are more complex, because we have come from random chaos into this highly evolved, organized organism, yeah, as a system, the entropy definitely decreased. But because of that, the entropy of our surroundings is going through the roof. So now we have two competing, I love reading different philosophies. One of my favorite books is by a man named Stephen Mitchell. It's called the Tao Te Ching. It was one of the, basically it's a translation of Sun Tzu, the Tao Te Ching, which he was Chinese, a Chinese philosopher. And you can get bad translations because in order to scare people about different cultures, there are some out there that are just racist. And they interpret different passages in ways that just sound scary, and it's terrible. Stephen Mitchell's interpretation is my favorite. And it talks about the yin and the yang, the Tao. A lot of people misunderstand the Tao. They think the dark principle is evil. The dark principle is not evil. It's just the dark principle. But they're opposites. And there's a little eye. There's a white eye in the dark side. There's a dark eye in the white side. Which actually is there to remind us that, you know what? There's a little bit of each on both sides. And all it is, these are the two competing principles for things that happen. Sometimes the yin is on top, sometimes the yang is on top. But they're constantly in flow. Nothing can occur without a yin and a yang. Well, that's kind of what the first and second law of thermodynamics is. Energy is the yin, entropy is the yang, or vice versa if you prefer. And they're in constant flow. Not conflict, but flow. And we're going to talk in one more video I'm going to make about the third law of thermodynamics. We're going to talk about how entropy and enthalpy, how we can figure out which one is on top and which one isn't. But until then, I am out of here!